Alright, so in this video we're going to introduce the concept of an elementary matrix. So elementary matrices, in some ways, maybe this is a bit of a stretch, but in some ways we can think of elementary matrices as the sort of building blocks of other square matrices in the same way that we might think of prime numbers as the building blocks of the integers, in the sense that if we take a bunch of any matrix that we might be interested in can be obtained by multiplying together a bunch of elementary matrices. Well, any invertible matrix, that is, with natural numbers, I suppose, if you want to obtain 0, there's only one way to obtain 0, which is you multiply by 0. But with matrices, we know that there are a lot of intermediate states between the 0 matrix and an invertible matrix, right? There's all the lower rank cases to deal with, and so that's why it's maybe not a perfect analogy. In any case, what is an elementary matrix? An elementary matrix is anything that you can obtain by applying one row operation to the identity matrix. So let's look at some examples. So if I start with, so think about doing, let's do some 2 by 2 examples, okay? So if I did a row operation like, switching row 1 and row 2, I could get an elementary matrix like so, right? All I've done is swap the 2 rows. I could do something like, let's say I take row 2 and I multiply by 5. Well, that would give me an elementary matrix of this form here, right? I could do, well, let's say I do something like row 1 minus 7 row 2. Put that into row 1. Right? That's another elementary row operation. Then we get 1 minus 7, 0, 1. Okay, so these are all examples of elementary matrices. In general, you'll find that elementary matrices are there's kind of these 3 types. We can think of these as type 1, type 2, type 3, in the same way that we classified the corresponding row operations as type 1, type 2, type 3. Right? So a type 1 elementary matrix, well, those ones you can spot by noticing that they're just, you have the identity matrix except there are 2 rows that have been switched. Right? A type 2 elementary matrix is one where it's almost the identity matrix, but one of those ones along the diagonal is equal to some other number. And a type 3 elementary matrix is one where you've got your identity matrix with 1s down the diagonal, and one of those zeros, one of those things that's usually a 0 in the identity matrix, has some other value, right? So that 0 in the top right-hand corner in this case became a minus 7. Okay? Anything that requires more than one row operation to get back to the identity is not an elementary matrix. So if I had more than one number along the diagonal that was not equal to 1, it wouldn't be elementary. If I needed to do 2 switches, it wouldn't be elementary. If I had something where the rows were swapped and I had, some other number like a 3 in here or something, not elementary, because I'd have to do 2 steps to get back to the identity. Right. If I have more than one non-zero entry off the diagonal, not elementary. Okay. The elementary matrices are very basic. They're very close to the identity because you only need one row operation to get from an elementary matrix to the identity. Okay. Now, the main reason why elementary matrices are interesting to us is that elementary matrices basically perform our row operations for us. We can think of them as sort of a bookkeeping tool. If we're reducing a matrix down to its reducer echelon form and we want to keep track of the row operations, we can keep track of those row operations by keeping track of the elementary matrices corresponding to those row operations. So for each row operation that we do that same row operation to the identity and we write down the elementary matrix. Right, so if we do some examples, let's work with our, let's take a matrix A. Let's do some 2 by 2 examples. So 2 minus 4, 7 minus 3. Okay. There's an elementary matrix. And so let's take the elementary matrices we had from the previous slides. The first one was this guy. So if we do E times A, 2 minus 4, 7 minus 3, and we just do the usual row times column procedure, right? Row 1 times column 1, 0 times 2, 1 times 7, 7. Row 1, column 2, 0 times minus 4, 1 times minus 3, minus 3. Row 2, column 1, 1 times 2 plus 0 times 7, 2. Row 2, column 2, 1 times minus 4, 0 times minus 3, right? And you can see that's exactly what we would have obtained if we had done the row operation of switching row 1 and row 2. If we had swapped the two rows of our matrix, we would get this matrix here. If we take this guy, it was did I put a 5? I put a 5. Okay. 2 minus 4, 7 minus 3. Okay, what happens? First row, 1 times 2 plus 0 times 7 gives me 2. And then 1 times minus 4 plus 0 times minus 3, I get minus 4. When I do the second row, first column, 0 times 2, 0, plus 5 times 7. 5 plus times 7 gives me 35. And then 0 times minus 4, 5 times minus 3, minus 15. And that's exactly what would happen if I took my matrix A and I multiplied row 2 by 5. And the last one we had was this guy, 1 minus 7, 0, 1, 2 minus 4, 7 minus 3. Okay, so row 1 times column 1, 1 times 2 minus 7 times 7, 2 minus 49. Gives me minus 47. 1 times minus 4 minus 7 times minus 3. So minus 4 plus 21 gives me 17. And then 0 times 2 plus 1 times 7. 7. 0 times minus 4, 1 times minus 3. Minus 3, right? And again, you can see that the result is exactly what would happen if I had done row 1 minus 7 row 2. And added that to row 1, right? If I take 7 times row 2, 49, and minus 21, and I subtract those from the 2 and the minus 4, right? 2 minus 49, minus 47, minus 4, minus 21, gives me the 17. Okay, so multiplying by an elementary matrix, and notice that it's one thing to keep in mind here is note that it is multiplication on the left. It's very important that this is always left multiplication. So if we multiply on the left by an elementary matrix, it's exactly the same as performing a row operation. Okay, good. Now, what does this have to do with computing inverses? Well, we know how to compute the inverse of a matrix, right? If we want to calculate the inverse of a matrix, we start with an augmented matrix like this, A on the left, identity on the right. We do a series of row operations to try to get down to this situation where we have the identity on the left and the inverse on the right, okay? And one way to kind of think about this, what you're doing is you start with A, the identity, right? And you're going to do some row operation. Let's call it, I don't know, row operation 1. Okay? So you do that row operation to A, and you also do it to the identity. So now we know that doing that row operation, well, that's like multiplying by some elementary matrix, multiplying on the left. Okay? And we do that to both A and to the identity, right? But then we could keep doing row operations. We could do a second row operation 2, right? So when we do our next row operation, remember that every time you do a row operation, you do it to whatever you had at the previous step, right? We don't go back to the beginning, we do it to whatever we had at the previous step. So the matrix E2 representing the second row operation, well, that's something that I multiply by the matrix E1A that I had at the previous step. And on the right, I've got E2 times E1, and well, times the identity, right? But multiplying by the identity does nothing, so we can leave it there. And then we continue on, and we keep doing steps until we get down to, well, some last row operation K. Okay, so at this point we've done, there's a K minus 1, E2, E1, right? We've already done these other row operations and we've got down to here, right? Notice that this guy here, I could write that as E2, E1 times A if I wanted to. Okay, I could move my brackets. And over here I've got my, oops, I've got the same thing, E K minus 1 down to E2, E1. And now I'm applying one more row operation, which means multiplying by one more elementary matrix. So I multiply both of these guys by EK. And I get down to here. Now, if this is the last step, then this whole thing here must be the identity. If our matrix is invertible, we know that the reduced row echelon form should be the identity. And notice what you have. You've got a matrix times A equal to the identity. And we know there's only one matrix that we can multiply by A to get the identity, and that's the inverse, right? And that matrix is this guy, EK minus 1 down to E2 times E1, and that's exactly what is sitting over here, right? So that must be our inverse, okay? So this shows us that if we want to, one way to kind of compute the inverse is to just perform row operations on our matrix, keep track of each row. So for every row operation that we do, we write down the corresponding elementary matrix, right? Keep track of all those guys. And then if we want to construct the inverse at the end, we just have to take those elementary matrices that we found and multiply them together. But be careful, notice the order, right? Notice the order. We have to multiply from right to left, right? Because the first row operation is going to be the one that's closest to A. E1 is closest to A, so it acts first, then E2, then E3, and so on. So we can build the inverse out of these elementary matrices as long as we're careful to multiply them together in the correct order. Okay, now this tells us a couple of things. One, every elementary matrix is invertible. Why is that? Well, let's just go back for a second. Let's go back to the very beginning. Okay, here are elementary matrices. Why are these things invertible? They're invertible because I can reverse each one of these row operations and come back to the identity, right? In this case, in the first one, what would be the inverse of this first guy? What's the opposite of swapping those rows? Swapping them back. So actually, this guy is its own inverse. And you can check that if I multiply that thing by itself, I will get the inverse. Let's call these things E1, E2, E3. What is E2 inverse? Well, I do the opposite thing of multiplying a row by 5. If I wanted to cancel out the effect of multiplying by 5, what would I do? I'd divide by 5 or multiply by 1 over 5, right? So if I, instead of multiplying by 5, if I divide by 5 in row 2, that should give me the inverse, and you can check that it works. How about the inverse for E3? Well, what's the opposite of subtracting 7 times row 2 from row 1? Well, the opposite of subtraction is addition. So we just have to change the sign on that number and we should get the inverse. And again, you can feel free to check as an exercise that multiplying those guys together gives you the identity. So this works in general. All right. So the reason why every elementary matrix is invertible is we just use the sort of opposite row operation. Okay. Now, why is every invertible matrix a product of elementary matrices? Well, once we know that every elementary matrix has an inverse, right? On the previous slide, we said that A inverse is given by this product, EK down to E2 times E1. We also know that A is the inverse of the inverse. So that's EK down to E2 times E1. We want to invert that guy. Well, we saw in the previous slide how to invert a product, right? The inverse of a product is product of the inverses, but you have to reverse the order. E1 inverse, E2 inverse, down to EK inverse, right? So if A is invertible, then we can write it as a product of elementary matrices. And the elementary matrices that we use are just the inverses of the elementary matrices that got us to the identity. Actually, this makes sense if you think about doing this algorithm, right? To reconstruct A, so let's say I reverse my steps, right? I start down here at the bottom. I start with this guy, identity on the left, A inverse on the right, you know. So the first thing I could do is I could, you know, let's say I kind of go backwards, right? So the first thing I would do is I would multiply by EK inverse times A inverse, right? And I would keep going. I would just reverse all these steps. I reverse the first step, which would be multiplying by EK inverse, then the next one, then the next one, and then finally at the end, the last thing I'd have to do is reverse the first row operation, which would mean E1 inverse. Right? And once I had done that, everything would have canceled out on the right, and I'd just be left with the identity, and so I get back to my matrix A. Alright, so we'll do a couple of examples in the next video showing you how to actually compute these guys.